Okay, hello everybody. Where is chat, by the way? Today is lecture 23. And section 23.1 is about, let's say, mean value theorem part 2. Theorems part 2. So last time we have proved Lagrange mean value theorem, and now some corollaries. So one corollary is rather important. So corollary of Lagrange theorem. It says if f of x, f prime of x equals to 0 everywhere on an interval I, then f of x is constant. On I. This corollary is very important to compute indefinite integrals, and so proof. Proof. So let x1 less x2 be arbitrary points of I. Then f is differentiable at every point of the segment x1, x2, because the segment, as we observe, as we suppose, is a part of our interval I, where the derivative is 0, hence the function is differentiable. Hence, f is continuous on x1, x2. So if it's differentiable at a point, then it is continuous at the same point. And all conditions of Lagrange theorem are satisfied. And Lagrange theorem says that there exists C somewhere between in the interval x1, x2, where the following equality holds. x2 minus x1. So that is by Lagrange theorem. Now f prime at C is equal to 0, since we suppose f prime equals to 0 everywhere on the interval I. Hence we have 0. And what it means? It means f of x2 equals to f of x1. And this is valid for arbitrary 2 points of our interval I, hence the function is constant. That's the end of the proof. So, one more example is another proof of inequality which we had before. Example 1 for today. That is sine x less or equal modulo x for all x in R. So we had geometric proof of that inequality for x from 0 to pi over 2, and then just by property of sine. And here is another proof. So proof. First case, x greater than 0. Then on the segment 0x, f of x equals to sine x satisfies all conditions of Lagrange theorem because it's differentiable and continuous. Okay. So, yeah, it's a little bit not a foreign name. Okay. So, hence, what we have? The function satisfies Lagrange theorem. Hence, we have sine x minus sine 0 equals to f prime at a point c times x minus 0, where c is on the interval. Now, what it gives? Derivative of sine we know equals to cosine, so we have sine x equals to cosine c times x, and we may put modulus sine. Okay, x is positive. I may omit modulus here. And we know that cosine is less or equal than 1, so less or equal than x. And the proof for x greater than 0 is complete. And for x less than 0, it's quite analogous, just interchange the order of the ends. Nothing else should be. Oh, sorry. Here I should put modulus, of course, right? So we have sine 0 minus sine x equals to f prime at c. Okay, let it be another c1 0 minus x. So we have sine x equals to f prime at c1 times x. So c1 now is between x and 0. And we put modulus. And we have, this is cosine, so modulo sine x modulo cosine c1 times modulo x less or equal modulo x as well. That is how, how the Lagrange theorem works. Okay, one more example. Example 2. How to use the Lagrange theorem for inequalities. So we have to prove square root of 1 plus 4x less than 5 plus 2x over 3 for all x greater than 2. So we proceed in a similar manner. we put f of x equals to square root of 1 plus 4x. So for the interval 2x, segment 2x, where x is greater than 2, we can apply Lagrange theorem for this function, because square root is differentiable for all positive values under this square root. And hence we can write, okay, I'll write in more details, maybe f of 2, f prime of c times x minus 2. C is in the interval 2x. So we substitute, we obtain square root of 1 minus 4x minus square root 1 minus 4 times 2 equals 2. Okay, what is square root? F prime at x is, by the chain rule, 1 over 2 square root of 1 plus 4x times derivative, and that gives us 2 over square root of 1 plus 4x. So we have 2 over square root of 1 plus 4c times x minus 2. So here plus, of course. So 4 times 2, 8, so we have square root of 1 plus 4x minus 3 equals 2. 2 times square root of 1 plus 4c times x minus 2. Now, if 1 plus 4c we know, because c belongs to the interval from 2 to x, is greater than 1 plus 4 times 2, and that is 9. Hence, square root of 1 plus 4c is greater than 3, and 2 over square root of 1 plus 4c is less than 2 over 3. So, if we apply this inequality to our equality, we obtain the inequality less than, because x minus 2 is positive by our supposition, we have strictly less than 2 over 3 x minus 2, and it gives square root of 1 plus 4x strictly less than 2 over 3x plus 3 minus 4 over 3, and that is just 5 plus 2x over 3 as we wanted. That's it. That's it. Okay. Now the last mean value theorem is Cauchy mean value theorem. So let me not good. So theorem It is called Cauchy mean value theorem. If f and g are continuous on AB and differentiable on the interval AB, then there exists C in the interval AB such that okay, f of b minus f of a times g prime at C equals to g of b minus g of a times f prime at C. That is the result. So, proof. Consider the following function. So, h of x will be just f of b minus f of a times g of x minus g of b minus g of a times f of x. That is, a function is defined on the segment AB and it inherits properties of the functions f and g. So it is continuous on the closed segment AB and differentiable on the open interval AB. Moreover, let's compute its values at A and B at the ends of our interval. H of A, okay, just substitute f of B minus f of A times g of A minus g of B minus g of A times f of A equals to, so what is it? We see that f of A, g of A, we cancel, it is with different signs, so we have f of B times g of A minus g of B times f of A. Yeah. Then look at the value at B then, right? So what is h of B? So we substitute B then. That is f of B minus g of A times g of B minus g of B minus g of A times f of f of b. Now f of b times g of b is in two places with opposite signs, so we cancel it and we have then what is with plus g of a f of b minus wait a minute, here is f, I'm sorry, yeah, minus f of a g of b. Let's compare f of b g of a, g of b f of a. Yeah, they are equal. Very good. So it means that h, the function h of x, satisfies all conditions of Lagrange theorem and Lagrange theorem. There exists a point C, hence, in the interval AB, where h prime at C equals to 0. And what is h prime? Here are some constants, so h prime of C is f of b minus f of a times g prime at C minus g of b minus g of a times f prime at C, and that is 0 according to our choice of C by Lagrange theorem. Where is chat? Где чат? Чат где? Да, я должен видеть, могу ли. Окей. Good. Okay, good. Good. And the last equality is precisely what we wanted to prove. Just put it in different sides of equality sign. So the proof is completed. Now, what is about geometrical meaning of the Cauchy mean value theorem? In fact, it's the same as for Lagrange. Why? Because we can, so I'll change the letter. So let's consider the Оно само, что ли, пропадает? So, let's consider functions f and g as or maybe in different order y, x, right? Then as we know, the derivative y prime x is nothing else but y prime at t over x prime at t, or f prime over g prime, right? Then, if we suppose that both multipliers with letter G are not zeros, then we can rewrite the Cauchy value theorem as f of b minus f of a over g of b minus g of a equals to f prime at c over g prime at c. What it means? It means that we have a value c between a and b such that this is the derivative of y as a function of x. And the derivative is nothing else but the tangent. Now, if we draw the curve given by parametric equations, parametric function, so that is precisely the curve with coordinates g of t, f of t, right? Then what is chord which connects the interval, which connects the ends? So here we have the point, let's say, g of a, f of a. That point has coordinates g of b, f of b, right? Then the tangent for this interval, the tangent is the ratio which precisely that one. So f of b minus f of a over g of b minus g of a. That is precisely the tangent for our interval which connects the endpoints of our parametric curve. And then what says the Cauchy mean value theorem? It says that for such a parametric curve, there exists a point where the tangent to that parametric curve is parallel to the interval which connects the ends of that curve. So, same conclusion as for Lagrange value theorem, but for parametric curves. And once again, as we saw for Lagrange mean value theorem, so we deduce Lagrange mean value theorem from Rolle theorem, but from the other side, Rolle theorem is a particular case of Lagrange. And here also you see that, for example, Lagrange mean value theorem is a particular case of Cauchy for g of x equals to x. So if g of x equals to x, then Lagrange theorem is a particular case of the Cauchy mean value theorem. Cauchy. So, all those three theorems are connected with each other. And one more corollary of, in fact, of Lagrange mean value theorem. I will not include it into a different section, makes no sense. So corollary 2 of Lagrange mean value theorem so if f prime of x is positive on an interval I, then f is strictly increasing on I. Proof. So we take arbitrary values, let x1 less than x2 be 2 points of our interval I. Then Lagrange theorem says that f of x2 minus f of x1 equals to f prime at c times x2 minus x1, where c is somewhere between. So is a point of our interval x1, x2, hence it's a point of our interval I. And since c belongs to I, the derivative at that point, by our supposition, is positive. Hence, so derivative is positive, x2 minus x1 is positive as well, so the right hand side is positive. And it means, so for arbitrary x1 less than x2, we have f of x1 less than f of x2. So we deduce the inequality f of x1 less than f of x2 from the inequality x1 less than x2. And that is precisely the definition of strictly increasing function on a set. That's it. And yeah, so for example, it gives us one more tool to check. As an example, look at the function x to the power n. So the derivative, okay, let's consider natural n. The derivative is n x to the power n minus 1, and it is positive for x positive, hence the function x power n is strictly increasing on 0 infinity. Okay, so in particular we used this fact to have if the function is strictly increasing, it has an inverse function, so it means there is nth root, well defined, and so on. Yeah. Okay, that's it, everything with section 23.1. So we can start next section. So 23.2, let's call that section Lopital. Lopital rule. What's correct writing? Lopital, yeah. Lopital rule. Or maybe let's call it case 0 over 0. So Lopital rule is an example of, how to say, author rights. So Lopital made something like he bought author rights to that rule from the author. The author was Bernoulli, and so it is called Lopital rule up to now. So yes, Lopital, yeah, it's correct. In fact, you know, it's quite, in French it is said Lopital, and there is another writing like that also. These are two versions of the same name, that's it. So it's just two versions of how to write it. But this is in French, what we can do. Lopital, yeah. And that is sound like that. Okay, let's have a break then. Что-то мне во вторник в КПМ холодно ужасно. So let's continue. So what's about Lopital rule? Let me formulate like a theorem. There is only one theorem in this section. So let f g be differentiable on AB x tilde is a point in our interval AB, f of x tilde equals to g of x tilde equals to 0, and g prime of x, g prime I said, is not equal to 0 in a neighborhood of x tilde. In fact, a punctured neighborhood, it's enough. So, in the neighborhood, maybe x tilde minus delta, x tilde plus delta, but without x tilde itself. We don't need to suppose that derivative is not 0 at the point x tilde itself. If limit as x tends to x tilde f prime of x over g prime of x equals to L, then the limit as x tends to x tilde f of x over g of x also equals to L. L need not be a finite number, so it might be an infinity, doesn't matter. So proof. Let's take arbitrary sequence xk's in AB, which has a limit k tends to infinity xk equals to x tilde. And yeah, I should also suppose xk not equals to x tilde. That's also should be supposed. So, then what we know? For sufficiently large, so there exists k natural, such that for all k greater than this capital K, all xk's belong to our punctured neighborhood. So they do not equal to x tilde by the supposition, and they will be in our neighborhood because of the definition of the limit of the sequence, right? Hence, g prime of xk is not equal to 0, and we can consider the sequence, so by the Heine definition, or sequential characterization of the limit, Heine definition, in other words, we deduce that the limit as k tends to infinity, f prime at xk over g prime at xk equals to L. So that is valid for arbitrary such a sequence, which tends to x tilde. Now, by Cauchy mean value theorem, if we apply it to the interval, okay, I don't know, either x tilde xk or xk x tilde, doesn't matter, we don't know the relation between those points, doesn't matter for which of them. So by Cauchy value theorem there exists a point C which is natural to call ck, which belongs to either x tilde xk or xk x tilde, doesn't matter. So there exists a point ck such that f of x tilde, okay, maybe alright, in this order, times g prime at ck equals to g of xk minus g of x tilde times f prime at ck. So for sufficiently large k greater than capital K, xk belongs to the interval where derivative is not 0. And in fact it is never 0 between those points, and it means that these brackets are also not 0. Why? Because suppose g of xk equals to g of x tilde. Then by Rolle theorem there exists a point, let's say c tilde, such that g prime at c tilde equals to 0. But it's impossible because xk is in the interval where the derivative is not 0. So contradiction. So it means the bracket is not 0, g prime is not 0, but f of x tilde is 0 and g of x tilde is 0 by the supposition. Hence, we can rewrite our conclusion of Cauchy mean value theorem as f of xk over g of xk equals to f prime at ck over g prime at ck. Now, by two policeman theorem, we know that ck is a point between x tilde and xk. Doesn't matter from which side. So it is between x tilde and xk, and xk tends to x tilde, hence two policeman theorem implies that the limit of ck is equal to x tilde as well. And we know that the limit then, so for arbitrary sequence which tends to x tilde, the values of f prime over g prime tend to L. So because of this and our conclusion from sequential characterization, we know that the right hand side tends to L. Hence, the left hand side tends to L as well. And what it means, once again, so for arbitrary sequence of xk's which tend to x tilde and such that all xk's are not equal to x tilde, we have the limit of f of xk over g of xk equals to L. So by sequential characterization or Heine definition, we have the limit as x tends to x tilde f of x over g of x is also equal to L. The theorem is proved. Okay. Now examples. Example 1. Find the limit x tends to 0 to x plus sine x over x squared plus 3x. Yeah. So find that limit. Here we have f of x 2x plus sine x, g of x x squared plus 3x. Both functions are differentiable everywhere on the real line. Moreover, g prime 2x plus 3 is differentiable, and g prime of x equals to 0 for x equals to minus 3 over 2. Hence we have a neighborhood minus 3 over 2, 3 over 2. We have a neighborhood of 0, where g prime of x is not 0. So all conditions of the Lopital rule for 0 over 0 are satisfied. Hence, we can write that the limit equals to the limit of the ratio of derivatives if this exists. So once again, that's very important, that how Lopital rule works. We suppose there exists a limit of the ratio of derivatives, then there exists the limit of the ratio of the functions, and it is equal to that limit. That is how it works. So if it exists, then so when we write like that, we should always remember this meaning of the equality. So we take derivatives, and we have then 2 plus cosine x over 2x plus 3. Of course, I forget to mention f of 0 is g of 0 is 0, right? This is also quite important. Okay, now we know cosine x is continuous, hence the limit is equal to cosine 0 equals to 1, so we may just substitute and obtain this equality. So we have computed. Okay, so next example. Okay. So example 2, find the limit as x tends to 1, 3x cubed minus 2x squared plus 4x minus 5 over 4x power 4 minus 2x minus 2. Once again, we have f of x equals to 3x cubed minus 2x squared plus 4x minus 5. G of x equals to 4x power 4 minus 2x minus 2. So f of 1 equals to g of 1. Let's check 3 minus 2, 1 plus 4, 0. 0. And g prime of x equals to 16x cubed minus 2. And that is 0. G prime of x is 0 if x cubed equals to 1 over 8 or x is 1/2. So it means that everywhere in the interval minus 1/2, 1/2, g prime of x is not 0. So, all suppositions of Lopital rule are satisfied, and we can write such an equality. Once again, remember that it is valid on the extra supposition that the right hand side exists. So we differentiate. Derivatives, okay, for g prime I wrote the derivative, 16x cubed minus 2. For f of x I didn't write yet. 9x squared minus 4x plus 4. Now, both functions in numerator and denominator are continuous, hence we can just substitute x equals to 1, so we have 9 minus 4 plus 4 over 16 minus 2, and it gives 9 over 14. 9 over 14. That is the limit. Okay. Right. X belongs to 1/2 3 over 2. Why? Yeah, right. Thank you. I forget. X tends to 1. Yes. Let it be like that. Yeah. Thank you very much. Yeah. I'm so sorry. Yes. You are right. Thank you. Yeah. We have a limit as x tends to 1, not x tends to 0. Yeah, I missed a little bit. Thanks. Yeah, okay. One more example, example 3. Example 3. The limit is x tends to 0, x squared over 1 minus cosine x. Of course, very soon you should get a habit to compute such limits in a different manner, but for a while let's use Lopital rule. So once again, f of x, x squared, g of x, 1 minus cosine x. Now, g prime of x is sine x. And we see that g prime of x is 0 for the points x equals to pi n, including 0, right? So our point x tilde equals to 0 is among zeros of the derivative. But by the conditions, g prime should be not equal to 0 for a punctured neighborhood. So it means that if x belongs to minus pi up to pi without 0, then g prime of x is not 0. So once again, this condition of L'Hopital rule is satisfied. And yeah, of course, I should also, f of 0 is g of 0 is 0. That is also satisfied. So we can write down equality x squared prime over 1 minus cosine x prime if the last limit exists. But look at this. What is it? So that is the limit to x over sine x. And we recognize here immediately the first remarkable limit, sine x over x, which tends to 1, so I can write like 2 over the limit sine x over x, and that gives us 2. So the right hand side exists, hence the left hand side exists also, and it is equal to 2 as well. By the way, we could proceed in a different manner. So suppose we forget about the first remarkable limit. So we don't know if the limit exists, but again we can proceed here by Lopital rule. So f1 of x equals to 2x, g1 of x equals to sine x. Now g1 prime is cosine x, and g1 prime is 0 for x equals to pi over 2 plus pi n and integers. So it means that if x belongs to minus pi over 2, then g1 prime at x is not 0. Hence, we can proceed for the second limit to x over sine x, again by Lopital rule. So that is limit x tends to 0 to x prime over sine x prime. Yeah, of course, one more condition should be checked also. Both are zeros, right? That's also quite important. So, lastly, we have the limit 2 over cosine x. Cosine is continuous, so we have 2. So even if you forget the first remarkable limit, you can proceed again by the Lopital rule second time. And in fact, quite often there are limits where you should use Lopital rules several times. There is a very useful example where you should use it infinitely many times, but it will be later. Okay, and now I think, yeah, last example for today. Yeah. Example 4. So here the question is about limit as x tends to 0, x squared sine 1 over x over x plus 3x squared. Yeah. So here the function f of x equals to x squared sine 1 over x is not defined at 0. So it has not, it is not defined at 0, right? But the limit as x tends to 0, f of x, as we can remark, look, this is infinitely small, x squared tends to 0, sine 1 over x is bounded, and the product of infinitely small function to a bounded expression is infinitely small, so the limit is 0. It means that we can consider, I'll use the same notation f of x as it is given in your lecture notes from the beginning, by the way. So we can define the function like that. Then the function f of x is continuous everywhere. Continuous everywhere. So, and f of 0 is 0, right? F of 0 is equal to g of 0 is 0, where g of x is, of course, x plus 3x squared. Moreover, g prime of x is equal to 1 plus 6x, and g prime of x is 0 for x equals to minus 1 over 6. Hence, for the interval minus 1 over 6 up to 1 over 6, we have g prime of x is not 0. So that condition is satisfied as well. There is one more condition which we didn't check yet, namely that f is differentiable everywhere. Clearly, f is differentiable everywhere except for 0, but what is about 0 is not clear. Let's check. That is indeed differentiable at 0. So, look, what is f prime at 0? By the definition, that is limit as x tends to 0, if it exists, of course. F of x minus f at 0 over x minus 0. So if we substitute f at 0 is 0, so we have limit as x tends to 0, x times sine 1 over x, and this is again infinitely small function times a bounded expression that is infinitely small, so the limit is 0. The limit is 0. So it means that the function f of x is differentiable everywhere. So all conditions of Lopital rule are satisfied, except maybe for the, so I'll write like that, but remember that in fact this is a conditional equality, right? So it is valid if the right-hand side exists. I said every time it, but now it will be quite important because look at what we have. So the derivative, okay, let's compute the derivative. So we have 2x times sine 1 over x plus x squared times derivative of sine is cosine times derivative of 1 over x, so minus 1 over x squared over 1 plus 6x. So what is it? Let me write it. What is it? Limit as x tends to 0, 2x sine 1 over x minus cosine 1 over x over 1 plus 6x. Now look, I can consider two sequences. Let's say xk tilde, not just xk, firstly, xk equals to 1 over pi over 2 plus pi k, k natural, let's say, right? So then the limit as k tends to infinity of xk, we have k in denominator, so this is 0, xk tends to 0. And the limit as k tends to infinity of, if we substitute into our ratio xk's, there is xk's, 1 plus 6 xk's. Xk tends to 0, so the first term in numerator tends to 0 as well. And cosine 1 of xk is cosine power 2 plus pi k is 0. So that is 0. But if we consider xk tilde 1 over, let's say, 2 pi k, k natural, then the limit of xk tilde will be again 0. But the limit of values, of our function, (1 plus 6 xk tilde). Now, once again, this tends to 0, denominator tends to 1, but cosine now, cosine is cosine 2 pi k, it's 1. So we have minus 1. So we have two sequences, two Heine sequences, which give us different values of the limit of values of that function. It means this limit doesn't exist. By sequential characterization. And it means that in fact we haven't this equality, because, as I said, this is a conditional equality. It is valid if the right-hand side exists, but it doesn't for our case. And what is in fact about our limit? Let's compute it. Nevertheless, without Lopital rule, because as we saw, Lopital rule is not applicable here. And we can compute nevertheless. So the limit as x tends to 0, x squared sine 1 over x plus 3x squared. I can cancel 1 multiply x, write it down like that. Now the numerator tends to 0, as we saw, right? And denominator tends to 1, so we have 0. This example shows that the equality in Lopital rule is conditional, in fact. And I mentioned it at every example once again. So the equality is valid if the right-hand side exists. And you see that this is an example where this if is not satisfied. Okay, that's all for today. Thanks for your attention. For good comments also.